All right, let's start. So I hope you can hear me well. I'm in a new place, so if at some point the sound becomes choppy or the video or so, just let me know. Okay. Thank you. Thanks, John. Okay, so today is the last lecture. So what I'll do today is, rather than introducing more technical things, I will just do kind of a wrap up. And in particular, we spend the whole lecture just talking about pure states, how they evolve, in different settings and so on, and within a lot of detail. And now in the last 2 weeks, we've been talking about all this new formalism to model uncertainty, for example, with the density matrices and maps that are not unitary and so on. And you might be wondering, well, how does this affect everything that we've talked about before? So that's what we'll be doing today. We will be just applying this formalism that we've done to kind of revisit some of the old settings that we've studied before. So in particular, we're going to look at the evolution of superposition versus mixtures. And for this, we'll recap a little bit of the particle in a box, but not a lot. And then in more detail, we'll go and study the double-slit experiment and see how we can analyze it using now this new formalism. And finally, we'll talk a little bit about weak measurements. I'll try to finish the lecture with giving you some pointers for what courses to take after, if in case you're interested in this. And because there's so much more I could have covered, but of course I cannot force you to study this for the exam or even to watch it. I want to upload a special lecture sometime in the coming weeks, where I'll put some things that will not be in the exam for sure, but I think kind of complete the course. So this will be the more technical one. Is this about quantum open systems? That would be the generalization of the Schrodinger equation for mixed states when we don't know everything about the Hamiltonian. So, for example, to model systems with noise. Then I'll talk a bit about quantum foundations, also because I imagine many of you who are not physicists took this course because you're interested in concepts in quantum theory more than calculations of specific settings. And then something that I wish there was a course at ETH just about this, but there isn't. And I think some people should talk about this. That will be about physics and ethics, and in particular, quantum physics and ethics, both a little bit of history maybe, and what now when quantum computing is around the corner, what are the ethical implications of this? So this will be kind of a fun extra thing. But now let's go to the material today. And so the first question is like, what happens if I have the evolution of a mixture of states instead of an evolution of a superposition? And this will help you really consolidate the difference between a quantum superposition and a probabilistic mixture of quantum states. Okay, so this is evolution of mixture versus superposition. So we're going to look at two cases. So suppose that we have a Hamiltonian, and we already found all the energy eigenvalues and eigenstates. So we can write the Hamiltonian, for example, if it has discrete eigenvalues, then we can write it like this, over n of the energy eigenvalue, and then the corresponding energy eigenstate. Okay. I'll give a specific example in a bit. So in this case, we saw that if we start with a state that is a superposition, well, we can always write an initial state and initial pure state as a superposition of energy eigenstates, right, in this basis. Then we saw that this evolves over time to of T to this superposition, but now each of these terms has a different phase, which is given by the energy eigenvalue, right? Okay. This is what we saw. So now the question is, what happens if we have a mixed state which starts, meaning not a superposition, but a probabilistic mixture. So probability Pn, I know I have the state psi n. So what does it evolve to? And just to motivate a little bit this, why I'd be interested is because we saw that in some cases, well, in many cases, this evolution here is highly non-trivial. So for example, the case we studied was the particle in a box. So I'll just recap the setting here. It's in more detail in the lecture notes. But so this was lecture 16. The potential was like this, right? It went to plus infinity between 0 and L. This is X, and this is of X, and this is plus infinity, right? And then we saw that the eigenstates were, maybe I draw it again. The first energy eigenstate was like this, and the second one was like so. And the third one was, again, assigned with a different period, as long as all the periods, each half period matched the length of the box, we were okay, right? So this was what we saw. And one way to do this is to say, well, we had that v of x, small x, was 0 if x was in the box. And it was infinite otherwise. And we saw, well, this is a limit case. It's not physical, but we then studied what happens if this box is finite. And we saw that the Hamiltonian was what? It was kind of p squared over 2 mu plus this potential. And then what we do when we diagonalize the Hamiltonian is to just rewrite it so in terms of the eigenstates, right? So this is essentially what we did in the lecture. Maybe we didn't write it explicit like this, but this is what happened, right? And in this case, we looked at the particular case of phi 0 being a superposition of these first two states. So this, kind of this plus this, right? And what happened in this case? So it was at phi 1 plus phi 2, square root of 2. Then in this case, we saw that the way it evolved in time was such that if you try to measure the position, so if you take the position wave function squared, like so, at time t, this was some constant which depended on x only, a constant that depended on x times some cosine of xt times another number, right? So let's call it c. In this case, and this resulted in the physical behavior that was highly non-trivial, because then what happened was the particle would go, if you remember, let me just write here, draw here the boxes. It was essentially bouncing, right, from left to right. So it would start something like here, and then it would be more equally distributed, and then it should be mostly on the right, meaning if I measure now, I'm most likely to find it on the right, and then again more distributed, and then it would repeat. It was a cyclical behavior. So in this case, having a superposition really meant that there was some non-trivial dynamics that are measurable, and in the limit of a very heavy particle, it really looks like a particle just bouncing back and forth, right? So this was the thing. So what happens now if instead of this state, I have a state that is of this form, a mixture? And I mean, first of all, there's many ways to solve this. One is just think about what this means. And this means I know with probability P I have this state, right? So suppose I prepared one of these states and then I forgot which one it was, right? It still evolves like just one of these states. So without the sum, so all it gets it will be a global phase. I just don't know what the global phase is, but it evolves trivially. But maybe because you're just introduced this whole notation and this whole formalism, maybe you don't have this intuition yet. So no worries, we can show directly that such a state would not evolve. Right? So how do we solve this? We have different options. The option A is to apply the Schrodinger equation for mixed states that we introduced last time. And this was what? So this was that the derivative in time of rho t is minus a over h bar, and then the commutator between the Hamiltonian and the density matrix at time t, right? Okay, but then we look at t equals 0. And in this case, h and rho, they are diagonal in the same basis. So if we look back, I will now go back to show this. You know, we wrote the Hamiltonian in this basis. So if you write the matrix, it's going to, in the energy eigenbase, just going to be this elements corresponding to the different eigenvalues. In this density matrix, it's also diagonal in the same basis, just with different numbers here that correspond to the probabilities of being that state. Right? So two matrices that are diagonal in the same basis will always commute. So then you can see immediately that this is 0. So then at time 0, d dt of rho of t at time t equals 0 is 0. So at time t equals 0, it doesn't change, which means that time at any small time, it will also not change, which means it just never changes, right? So then rho of t is rho of 0 for t. And like I said, we gain, of course, if this corresponds to one of the states is prepared with probability Pn, then it will get a phase. I just don't know then what this phase is because I don't know what the exact state was. But what happens is that this global state doesn't matter for any local experiments, right? And my density matrix is the only object needed for local evolutions and local experiments. So this phase is not contained in it. We can make this even more explicit if we look, if instead of doing the Schrodinger equation, we just apply the unitary evolution directly. Okay? So this is a different way to get to the same result. So apply directly this. Meaning what? So I have rho of t. We saw how density matrices evolve. If there's a unitary evolution, I need to apply the unitary before and after. And what is the unitary here? It's the exponential of the Hamiltonian, right? So this is a matrix still. But it's a matrix that's diagonal in the same basis as the density matrix. This doesn't matter, so we can write it like this. So we have e to minus I h t over h bar. And now comes our density matrix, sum over n. Pn and n. E I h t over h bar. Everything is linear. And Pn. E I h t over h bar. Okay, but this we know what it is, right? Because psi n is an eigenvalue of the state of the Hamiltonian, so we know that this will just return psi n again, and now the eigenstates is minus, the eigenvalue is minus ETH bar, and then here the n. Right, and the same here on the other side. So I get sum over n, Pn, E minus IT, En over bar. And it's the same on the other side, except here I have plus I nt over h bar. And now these two exponentials cancel each other, right? They're just the inverse of each other. So then I'm left with my original state. Yeah. And again, I mean, this is one way of seeing that the density matrix does not include any information about the global phase on the whole thing, because it's not relevant for physical experiments, for local experiments. Okay, so this was density matrix. And then you may ask, okay, but how is this not a problem for the superposition? Let's write this superposition, which is a pure state, also as a density matrix, and then apply the same formalism again to see why one evolves and the other one doesn't. So now, this is we write this mixture, the superposition as a density matrix. Just to have a look at, just to see exactly what the difference is, right? So then we have, let's give it a different name. So rho tilde of time equals 0. And now this state was this equal superposition. So m of not equal, but any. And then we have it on the other side as well. So let's give it a different name. And because it's the transpose conjugate, now it's the conjugate of the coefficient. There we go. Oh, this first sum should be over n. So now we have a sum over n and m of alpha n, chuk, phi n, phi m. Now this is no longer a diagonal matrix, and we have a sum, right? So we'll just split it into two parts: the parts where n is the same as m, and the parts where it's not. So when n is the same as m, we have n, and then we have this thing here, which for the same coefficient is just a number times the complex conjugate. So it's just alpha n squared. Plus the sum over all the m's and m's that are different from each other of alpha n alpha squared. Right, and this now looks, this part here, let's call these are the diagonal elements. Okay, so this looks like alpha 1 squared, alpha 2 squared, in the energy eigenbasis. And this is the off-diagonal element. So all the diagonal is 0, but everything else you have here, alpha 1, alpha 2, alpha 1, alpha 3 star, and so on. So all of this are non-zero, right? So then we can look at the two ways of solving the time evolution that we saw before. One was applying just the Schrodinger equation now for density matrices. Right. So when you do now d dt of t equals minus I over h bar, the commutator, and now we do the same for time equals 0. And now this is, so h of 0. I split this matrix into these two parts, so I have h, the diagonal part, plus the off-diagonal part, right? And the commutator is linear, so it's, we get h, the commutator of the sum, so commutators, so we get diagonal off diagonal, right? And this one is 0, because again, they're matrices that are diagonal in the same basis, but this one is not 0. And it's this off diagonal elements that give us all the interesting dynamics. Right? This is the part that leads to non-trivial time evolutions. You can also, okay, I will not do it explicitly now because it's, so this was doing A, and because it's a lot of computations, but you can do now what we did before, that this is going to be U of t, rho of t, U of t, sorry, rho of 0, U of t dagger. And when we do this explicitly, even if you expand this row like this, like we did here, into all these terms here, of course, what you end up with is that this is U of t. The initial state, U dagger of t, and that's just still a pure state, right? So if you look at what I wrote in the lecture notes, is to do it explicitly. But of course, like if you start with a pure state and you have only unitary dynamics, reversible dynamics, then you must end up with a pure state. Okay, this is always true. And I think this example is quite dramatic. So if, in the case of the particle in the box, if you put in a mixture of these two first states, right? If instead of a superposition you put a mixture, it really does not change in time. Okay. So now, I wanted to look at the double-slit experiment once more. And we'll look at again at it through the lens of density matrices. So we can now bring together some of the elements we just saw. So again, just to recap, what happens at the beginning of the double-slit experiment is that you have some wave function that is a superposition of this left and right, and then they evolve in time, and depending on what they are, you then here you'll see some interference effect when this particle hits a screen there, right? So to be more clear, at time 0, you had an equal superposition of left of 0 and say right of 0 over square root of 2, and this evolves, and there's some unitary, so that at some time t, you have now the superposition of this plus r of t over square root of 2. And now, if you write it as a density matrix, this is like before. It's a pure state, so it's just the cat and the bra multiplied, which will give you 4 terms, right? And then when we do what's the probability of finding the particle at a position x here? This corresponds to a measurement px. So the probability of x at times t, this is trace of, so px, it's just, in the ideal case, it's just this, so it's x rho of t. And this is trace of unit density matrix formalism is this of t. And you know that we can write this as, because the trace is cyclic, you can write it like this. I can replace here the rho of t already with what it is. Right, you move one of these vectors to the other side. You get that? Okay. And now the basis for the trace, you can choose whatever you want. So you can choose the position basis again. So anyway, this just gives you xi of t, xi of t, which is, as we know, per usual, right? It's just the wave function squared at position x, right? But then, what is this? I mean, now if you replace here this psi of t with what it actually is, with this superposition of left and right, we show this already, that what you get in the end is that this is, it's a bit large, so I write it here, so it's 1/2. So you get the probability as if it was only the left branch of the wave function evolving, plus if it was only just the right, plus all these superposition terms, right? So so this we did explicitly before, right? R of x and t. Okay, but now the only thing we did was not to put here the row explicitly, but then it immediately, we can write it again in terms of pure states, and that's it, right? So now what happens when we measure which slit the particle went through? And we said, well, we can model this as, so here goes the particle through there and there. And I just put here a little, my pointer can be, for example, a spin that detects this particle coming here. And if the particle goes through here, I mean, it flips the spin, right? This is a unitary evolution. So what happens in the beginning is that I have psi L, psi right on my particle P. This is the yellow particle, square root of 2, this whole thing. And 0 on the spin. And this evolves, this is a unitary evolution interaction to correlate the two, right? Just psi right and 1 here. Okay. And then what we saw using just the pure state formalism is that now, if we now let the system evolve, let only the particle evolve, we leave the spin alone, then the pattern we encounter at the end is less of a, there's no interference effects, right? It just looks like the kind of probability distribution we'll get if we have just a particle going from the left plus just from the right. And now one very easy way to look at this is to see, well, we had this unitary map on a larger system, which is the particle and this spin. So what happens if we now look just at the effective map, the reduced map on just a particle. So we call this thing of 0 of particle and spin. So could write this rho of 0 of particle and spin. Just this, right? Chook. And what I could have done was to see, well, what is the effective map of just on the particle to the particle of just my initial state. So tilde, 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 tilde. So what was the state I had before this interaction? It was the same as before, right? It was just my rho of 0 in the P as before, meaning just this state, right, for time equals 0. It was just this. So I can write it like this. So what is this? Well, it's a Stein. If I look at the Stein spring dilation, so it's a partial trace over the spin of what? Well, of my initial thing, tensor, the 0 that I brought in the spin, right? And then all of this thing evolved over this interaction unitary. Right? So this is the global evolution. Now I'm just looking at what happens locally to the particle. So this is going to be trace over S of my matrix that I computed now. Right. Okay, so now we look at this. So rho P 0 tilde. So this is trace over S of the state. And what is the state? So we had psi L 0 plus psi right 0 square root of 2 multiplied by psi left. Oh, sorry. This should be a 1. 1 plus right 1 over square. Oh, this should be a 0. I go. Okay, so 1 over 2 trace over S, and now we have these 4 terms. So let's just take first this and this. This is just psi L in the particle, tensor 0, 0, and my spin. I say spin, but it could be, any qubit. Plus left and right in the particle, tensor 0, 1, plus right and left in the particle, tensor 1, 0, plus right and right, tensor 1, 1, right. Now, if you've done a few partial traces by now, what's the partial trace? So this is just going to be the sum over all k going from 0 to 1 of identity and the particle tensor. K on this side, and here identity in the particle tensor. K on the other side, right? In a spin. So if you've done a few partial traces by now, you know that what it does, it will kill off all these off diagonal terms, for the simple reason that if I put here k and k, you have these two inner products and they you know, if this is 1, then this one will be 0, and vice versa, right? They cannot be 1 at the same time. So only the diagonal terms survive, meaning that you have the same ket and bra on the second system. I did explicit in the lecture notes if you want to look at it, but here for the sake of time, we just write the results. So this is 1/2 of L plus psi, right? And now this is familiar to the thing we had before when you talked about the evolution of the particle in a box, right? Of general states, because now I know how this evolves under local evolutions. But now let's just write again this diagram where we do the partial traces to see how it all fits in. So we started with notation slightly different. So we had this row. We had row P, M0, 0, right? We had this initial state. Then there was this U interaction, right? And we got this row tilde PS of time 0, right? And what I did now was to take the partial trace over S to obtain just the state and the particle, right? And this is the same as doing here just a map, right, on row P. Okay. Now, this thing is going to evolve under what? Some evolution of time that depends on time in the particle. And we said we leave the spin alone. But even if we don't leave it alone and something is happening to the spin, as long as it's still of product form, you know, something is happening somewhere else to it, there's no interaction between the two again, then we know that if we did the partial trace here, right, this is the same as just evolving this one over this unitary just on P, right? We only need to evolve the reduced state to P of time T, right? And now if we make a measurement, a local measurement, right, where here we just do the trace of, say, pi x times the state to get these probabilities of x, rho tilde of t. This would be the same as modeling it as a global measurement, or modeling this global measurement as a this local measurement as a global operation, right? So we can do this, meaning that we did this, and now we can continue everything with a reduced state. So what's this local evolution? So now let's do this local evolution. And now we know already this, right? It's going to be U of t 0, U of t dagger. Then we know, well, I'll just write it again. What this was psi L of time equals 0. Okay, I just don't want to write it again. R ut dagger, and just like we saw before, now these unitaries act on these individual states. So what I get is just obviously a mixture, a probabilistic mixture again. 2 plus okay. And now I'm again in the same case, right? Because now if I do the if I ask now, what's the probability of finding the particle at position X for this evolved state? Right, now this is trace of pi X rho of the particle, but the trace is linear, so I'll end up with 1/2 of trace of pi X. And here comes the left. Plus 1/2 trace of pi X, and here comes the right one. So, and this we know for each of them, this is just psi L of t squared plus 1/2 of psi right of t squared, right? This is easier, I think, than what we did before. We had this formalism of density matrices where it took a bit more work to get to the same result. Right, so what we don't have here is all these cross terms that characterize the interference. Right. Okay. Yeah, so if we wanted to tie back this to the previous example, so I have the particle in a box. Suppose I have the nice superposition of the first eigenstate and the second eigenstate. So it's really bouncing left and forth, back and forth, right? So how do I transform this into a boring mixture? I can, for example, measure the energy of this particle, right? By measuring the energy of the particle, what I'm doing is essentially this interaction here, right? So it's essentially this. It should be like, oh, I have psi 1 plus psi 2 and my measurement device, and I'm doing a measurement of energy. So now what I have is psi 1 1 plus psi 2 2, right? So in my measurement device, it stores which of the eigenstates it was, right? And now suddenly I have a mixture, which means it will stop evolving in time in an interesting way. So this tells us not only about the difference between superposition mixtures, but really how physically to go from one to the other. If you wanted to go back to a nice superposition, then you need to reverse this measurement, right? And reversing this measurement, it's very easy. As long as it's only these two particles, you can do this. But if now you looked at the measurement device already, that means that now your whole brain is already entangled also with this qubit here, right? So now there's a very big state here. And now reversing this would mean applying a very precise unitary, not only on the spin, but also all of your measurement devices and the screen where the result appears, and your eyes and your brain, and everyone you've told about the result, right? So it's very hard to keep track of all these correlations, which is why effectively it looks like an irreversible operation, right? Because as soon as you trace out any of these degrees of freedom, it looks like a non-unitary map. Okay. Okay, we have to finish here. So about the case of weak measurements. So what happens there is when here you do this kind of thing, but the states in your pointer are not necessarily orthogonal. There could be some overlap between them. So then when you take the partial trace and look at just the system that was measured, then you don't get this this total killing off of the off-diagonal terms. You can preserve some of them. So I'll put this in the extra lecture. You also did a little bit of this in the tutorial today with one of the exercises, the one with the control rotation. So I'll put this in the extra lecture, and then it will not be in the exam, right? Because of the weak measurements. So I just wanted to tell you what, if after this lecture you're still interested in quantum mechanics, what can you study more? And in particular, if you're at ETH, what are the courses you can take after? Okay. So if you want to learn quantum computing, take just QIP one concept. This is taught by Philip Carmelander. He's an excellent lecturer. The course is very easy. If you did all of this, seriously, you can do it in 1 week. And it's just going through quantum algorithms and then again using the density matrix formalism to talk about error correction, how you correct for noise in quantum computers and so on. If you care about quantum information in general, then you should take QIT. This is in the spring semester. If you care about foundations, and also some more aspects of quantum information, then you can take advanced topics in QIT. I'll be teaching this in the spring semester with Ralph Silver and a guest lecturer. And this you can take already as well. You don't need QIT. If you took this course, you're good to go. We'll do some thermodynamics, some foundations, maybe a bit of quantum learning theory. If you want to continue studying physical statics, so this you can do QM2. And again, I think you have all the basis to follow that course, and it will be taught by Renato Renner this semester, which means he'll put a bunch of foundations in it, and yes, this information theoretical background, so an inclination. So it will be fun. It's just in German. So if that's the problem, maybe it's not the best. Okay. And these are just the beginnings, the next steps. I cannot imagine following this course this long and not wanting to know more about this theory. But if that's the case, you're done. I think you've learned enough. I'm happy with everything we've covered. And again, I'll add some more things as extra material later. So thank you. It's been a pleasure and happy holidays. If you have questions, I'm here now.